So any questions before I go forward? If not much, so I will start now. So we have, since last week, we have begun looking at two species systems, right? So we looked at competition between two species, okay? And one fundamental thing sort of, take away from what we learned last week, both from Lotka-Volterra model as well as model, consumer resource model. Coexistence is basically possible. If there are two species that depend on the same resource, competitive exclusion is basically norm, and coexistence can happen under very, very special circumstances, and therefore, one on a given resource, two species cannot really coexist. Of course, in real world, you do see that many animals and species do coexist on smaller number of resources, but that's where understanding what do we mean by resource is important. It's not just what is the resource, it is also how you are consuming it. For example, you may have the same resource, but two species might be utilizing it partitioned by time, partitioned by space. Okay, so those are all, of course, ways. Effectively, although it is the same resource, the way you consume basically becomes different, and you create your own niche, that others cannot. Species coexistence. There is an entire field called community ecology. And I think other ecology courses cover those topics in much more detail than I can do here. Okay, but in fact, one can extend the mathematical principle we derived last time. If on one species only one, on one resource, in general, only one species will exist. Okay, what if we had n resources? What do you think will be the maximum number of species that can coexist on n number of resources? The answer actually can be mathematically derived, and it turns out that when you have n species, you can have a coexistence of maximum of n number of species. You cannot, only which are all competing with one another for the same, for the same set of resources. Okay, so and so it does turn out that there are ways that more than n can also survive, except that it cannot be via competition only. Okay, so but if the competition is the major mode of interaction between species, then for n number of species, in n number of source, maximum of n number of species can coexist. Okay, now having studied competition between two species, let us now look at another classic predator prey. So let us write down equations, right away. We are now, I'm hoping that now you're all sort of, comfortable being able to think through equations for these kind of systems. So how do we write down, expression for prey dynamics? Okay, let's denote prey by n. Let's denote predator by P and prey by n. Okay, so then dn by dt. So what are the terms in this going to be? The rate of change of population of prey. So if you were to think about it in some simple way, one is, what would it be in the absence of predators? Okay, that's the growth rate. Not just growth rate when predators are absent. And then what happens when predators are present? There is some death rate because of predation. Is that correct? So in some sense, this question is very similar to the harvesting, models we discussed, right? But when we discussed harvesting, we just ignored the dynamics of predator. Now we will explicitly do. And in fact, some of you back then even wrote down what could be the equation for the grazers or the predators. So the rate of growth of predators are the grazers, it could also be thought of as grazers, is that, there is some depth. By the way, just to be very clear, this is the total rate. This is not per capita death rate, right? So because the left-hand side is total population growth rate, so everything is in terms of total growth rate and total death rate. Okay. So what we have is some conversion efficiency times death rate by predation. So the better way of death rate by predation is same as consumption by predators, right? Death rate or consumption. So when you're writing this looks a bit awkward. Growth, okay, minus death rate of predators. Is this fine, everyone? Is this broad set of equations fine? What are all going? What are the processes that are going in to describe the dynamics of prey and predators? I just want to hear an yes or no because I haven't had any noise since the beginning of class.
Oh, yes, sir.
Thank you very much. Okay, so now let us do the following. Let us use some notations that we have been sort of using. So now writing it for prey, let us write that the growth rate of prey is f of n. Okay, so this term we are calling f of n. And this term, let us call, what will this term be? Just think about this. This will be basically, let's denote this by, going by our sort of, harvesting notation. Let us call this by h. It also depends on n, depends on both n and p. So like the harvesting rates the predators, it depends on both the number of predators.
A small doubt. For the prey, we assume f of n to be some sort of logistical growth, right? So for the predator growth also, shouldn't we assume some kind of like saturation with that rate prediction?
It is possible. One can actually
like
write that way also. You're right, absolutely right. There are two ways to write these equations. One needs to account for how the conversion actually is happening between predators and prey. That's one way of writing. This is also called I think the Lotka-Volterra formalism. Okay. However, what you are saying is also possible. You can directly write down something like a logistic growth for both of them. Okay. That's also possible. Absolutely possible.
We can write something like Holling's function, no? For second.
Absolutely right. You're absolutely right. Yes. Absolutely right. Yes. So I'm just writing, initially just the notations. Okay, and then we can, Okay, so here, f of n. So h actually comes here with some conversion coefficient. So what symbol shall I use? My only worry about using gamma is gamma will look so similar to R in my writing that I will mess up my entire writing. So maybe I will choose what shall any symbol you like. Here is your option to tell me. If you don't have, I'll just write some.
Beta.
I don't. Okay, I can write beta. Let's then make sure let's not use beta anywhere else. Okay, I think we can avoid using beta anywhere else. So that way we can also try to map onto sort of since we haven't used alpha, why not alpha? Or we can actually use alpha here in the previous.
C or something conversion.
C is also fine. Yeah. You can use actually right. Yeah, we can. So harvesting H will keep the H 0 like the previous one. Okay. So this I will call C then. There was some reason why I thought C was a bad idea, but it's not. And then this becomes D now, death, right? So this becomes a death rate. So this some function D of n. Is that fine? This is the most general form. Is that fine?
Shouldn't that be
T
D
of
of
P,
P?
no?
Oh, you're right. The only reason again I slightly don't like D is we're also using D for differential, but I think you can distinguish the two, right? Okay. So maybe I won't. Okay, we use D here, but maybe I will. Okay, this is just exactly same as above, but with some notations. Okay. Now you are all now experts in model. Now you know how to sort of play around with this, right? You can for each f, basically f, g, f, h, and d are the sort of three functions we have, and then and there are there are many different forms we have already studied for what are all possible. Okay, and then let's go one by one. Okay, so let's call model 1. Which is also called the Lotka-Volterra model of predation. Okay. F of n is assumed to be just A of n, which basically means density independent growth. Okay. In the absence of predators, basically the prey will grow exponentially. Okay. And okay. And basically predators, not what this basically means is that it is not that the resources are infinite. It just means that predation is the dominant force that actually will limit the population of prey. Okay. And now going to H. H is harvesting rate by predators. Okay. B times N times P. Okay. Which basically is a product of the number of prey one, right? Yeah, Holling's type 1 form. Okay, and then we have D. N. Okay. So this is called the Lotka-Volterra prediction model. Let's just write this down. This will lead to something like this. AN, sorry. Minus BNP. BCMP minus D of P. Sorry, this D is a function of P again. So this is called the Lotka-Volterra predation model. So basically comments are, it's basically Hollings type 1 functional response for the predation. And predators are the limiting factors. Predation is the limiting growth factor for prey. Okay, and all the parameters are positive. All of them are positive. Otherwise, we'll be studying some trivial scenarios, or even not so biological scenarios. Any questions on this? So this is model 1. Now let us look at another model. So I think the model 2 is just called Volterra model. So the key difference, I'm only going to write the difference here. In the Volterra model, the assumption is that the intraspecific competition, is explicitly incorporated for prey here. So therefore, actually write something like this. Okay, this is the major difference, and this will basically now make the equations as follows. As you can clearly see, this is a lot more B of NP and then dP by dt is equal to BC NP minus dP. Okay, let me now describe the another important model. Now, okay, now let me just make sure I get the spelling right. This is the okay. I had to really Google this. I'm so sorry. I should have checked the spelling. Rosenzweig MacArthur model. Okay. So here, the basic idea is that the F continues to be logistic as before, and H now becomes Hollings type 2. So basically, I'm just listing 3 important models in the order of increasing complexity and more biological realism. Okay. B NP divided by N0 plus N, is that right? BC NP divided by minus dn. Oh, dp. This is fine. Any questions? Okay, so let's try to analyze some of these now. How do we understand what are all the possible dynamics of such predator-prey models? Okay, and as you can see, the mathematical difficulty increases here. It's not, of course, something extraordinarily complex. It's just a little more algebra than what we have been doing so far. Okay, so let's do model 1. So before I go forward, do you all now feel comfortable that you're this stage of the course, almost about just a couple of weeks more? Do you feel comfortable looking at these equations, making sense of them? What kind of difficulties do you face? Or is it all clear now? I hope everything is clear now. Okay, so dn by dt is an minus bnp, okay, and dp by dt bcnp minus dn. Okay, so there we are. So how do we go about this? I'll remember, look at this again, phase plane analysis, right? Where we draw null lines. Equilibrium is given by setting the right hand sides equal to 0. Okay, so let's do null lines. For a null line for n dot is equal to 0, what would that be? So you basically can either have n is equal to 0, right? Or if you take n as a common factor in this right hand side equation, you have a minus bp is equal to 0, right? Or p is equal to a divided by p. Is that clear? I did not write the equation explicitly. All that I've done is in this equation, I have taken n as the common factor. Okay, and then what you have is n into a minus bp is equal to 0, right? So this you can get 0 by either setting n equal to 0 or this equal to 0. And those are the two null lines that I have for n dot is equal to 0. Okay. Now let us write down null lines for p dot is equal to 0. Again, do the exact same process. Here, oh sorry, this is p. I don't know why I'm repeatedly doing this mistake. Here we take p as the common factor. What we then have is bc n minus d is equal to 0. This will give us two null lines. P star is equal to 0 or n star is equal to d divided by pc. Is that right? Have I made any mistakes? There's some, yeah. I think I began the recording, right? Yeah, it is recording. Yeah. Oh, I hope it is recording. Is it?
Yes, it is.
Okay, it is recording. Yeah. Okay. So these are the two, 4 null lines, 2 for each of the 2 equations. So let us now plot the null lines. So we will write prey population on the x-axis and predator on the y-axis. Okay. So let's again, like the previous class, write the n, one of them by blue color, other by this I will use blue and this I will use red. And I will mark the equilibrium by green. Okay, so n dot is equal to 0, n is equal to 0. N is equal to 0 is this. Okay, and then we have P star is equal to A by B. Let's say A by B is some constant. Let's P star is equal to A by B. This P star is equal to A by B. This is N star is equal to 0. Okay. I shouldn't call N actually stars because it's not equilibrium. Equilibrium happen only when they intersect. Now let me plot the null lines for this. So P is equal to 0. P is equal to 0 is this. And then we have N is equal to D by BC, some value, some constant value. So this is P is equal to 0. This is N is equal to D by BC. So now the equilibrium are wherever they're intersecting. So there are two places where the red and blue lines intersect. That's one is here, one is here. Okay. So we can intuitively guess what should be the 0-0 equilibrium. So 0-0 equilibrium, one at the bottom left corner, is an extinction equilibrium where both A and B are 0. Now, if you make some perturbation, because A is positive, right? I have said that all parameters are positive. Then A and it will begin to grow exponentially, right? The moment N grows, P will now grow because they're consumed. So this has to be unstable. But what about this? That's not very clear. Okay, so let's do what do we call as this the direction of flow in this area. Okay,
Vishu, I didn't understand the previous point, how this is unstable. This
so this is an extinction equilibrium, right? Okay, and let's say now I introduce some perturbation, which is there is some amount of N and some amount of P. Okay, because A is now positive, it will begin to grow exponentially. Okay, and when N grows exponentially, P will then increase as a consequence. Now, what you might be wondering, how isn't it possible that predators will basically over consume and therefore things will go extinct? So that you cannot really, unfortunately, in this case, this is not as simple as a one-dimensional case. You can easily, whatever I have just said could have been verbally wrong. Verbal argument I just gave you could be potentially wrong, because even though N is initially increasing, it's possible that predators will consume them and therefore drive N to extinction, which may then drive P to extinction. That is actually a possible scenario, but the only way to know that really is by analyzing the Jacobian of the equilibrium. It's not possible to know just by verbal arguments.
Okay.
So you really have to do. We will do that. Okay. Before we do, we'll just do some, what we call, try to see how is the overall flow. Okay. So in this region, let's say anywhere in this region, what's happening, right? So I am below this blue line. I am below this red line. Right. So, but here it's a bit tricky. The way the entire Lotka-Volterra model runs is quite tricky. Okay. Let's say we are here in this region, which means I am below. So P is less than A by B, right? Which means this term is positive, right? And N is positive. So both of them are positive. So therefore, prey will continue to increase. So prey will continue to increase. Is that right? That does happen. Now, what happens to predators? So predators, just look at this. I'm below, N is below D by BC, right? So therefore, so N is less than B by C, right? Is that right? So when N is less than D by C, just look at this term. This is the time I'm trying to focus now. So we have B, C, N minus D, right? Now, if n is less than d by bc, what happens to this term? Okay, so this term will be less than d by bc times d by bc. Is that right? So this term will be less than this. BC cancels. Therefore, this term will be less than d. Do you agree? So the first term here is less than d. Second term is d. So therefore, this entire term will be negative in this region. Do all of you see that? So by the way, just to make my point clear, I'm going to write this flow here. So we are clear from this equation that n is increasing because this term is positive, this term is positive. Now let's look at the p dot term. P is positive. This will contribute to a positive term here. But this entire term is a negative term. So the product of that will be negative, right? So this is P is reducing. Do you all agree? This is a bit counterintuitive compared to what happens in the previous model. So therefore, we have to check this carefully for every model. Okay, and what will be the, so net flow will be something like this. So it's not very clear whether it's going towards this equilibrium or this equilibrium, right? Is it clear? It's not very clear. Okay. Any questions on this?
But biologically, the rate of prey and predator need not be, somewhat proportional, right? I mean,
they need not be same. So you're right. You're absolutely right. Yeah. Then the rate need not be same. So therefore, we don't know if it's the rates were identical. Then it would be like a circle.
Yeah.
Then it could be now. It could also be more of an ellipse. So without what we don't know then is whether it's actually how bent it is, how much bent that is. That we can only have to numerically evaluate. That's the only thing we can do. But this is to get an intuition of what is happening in this entire, population plane. This is also called a phase plane analysis. This is to get an intuition of what are the possible scenarios. Okay. But what is evident is that this is clearly not going towards zero for sure, right? It's not like going to see. So by the way, whatever the diagram I have written, it's true in every part of this square rectangle. Do you agree? Whatever I have written is true in every part of this rectangle, right? It's not just this specific point. But of course, the exact flow and the bend might be different. Okay, now let us look at what happens in this region. Okay, so I have written this too big. Let me make it a bit small. This n is equal to d by bc. Okay, now again, what happens to n dot in this region? In this region, it's below this blue line again. It continues to be this way. What happens to the predator growth in this region? It was negative here. You can just argue it has to be positive here, right? Because now n is more than d by bc. So therefore, this will take the exact opposite sign now. So the first term will be greater than d. So therefore, this term will be positive, right? So here the predator is increasing and preys are also increasing. So therefore, the overall flow looks like this. Is that fine, everyone? Okay. Now let's look at what's happening in this part. In this part, what happens to dn by dt? Now I'm above p is equal to a by b. Therefore, this now p is now very large. Therefore, this term now becomes negative. The n dot is now negative. So it's in this direction. What happens to red? Prey. Predators, are they still increasing? Predators in this part. See, remember that predators will be increasing in the entire right side of this red line, right? Because the number of prey are large. So therefore, this term will be large. Okay. So consequently, you have now have flow like this. Is that fine? So in this part, the n is very large, prey are very large. Therefore, predators are increasing, but the prey themselves are reducing. Okay. Finally, in this part, what's going to happen? So in this part, again, because the predators are very large, okay, prey will reduce. Okay, what happens to predators themselves? Here, predators also reduce in this region. So both of them are reducing. So the reason why prey are reducing is there are too many predators. The reason why predators are reducing is there are the number of prey are not enough. So this is the overall flow. Okay. Is this clear to everyone, by the way?
Yes, sir.
Okay. So now basically what you are seeing is, when you are in the, let's now start with the lowermost quadrant. Okay. So, if I were to now make a sort of a, some kind of a possible trajectory, what might be happening is, a predator and prey population here will get pushed. Maybe this and maybe go up, right? I'm just following all the green arrows now, okay? And come down, right? Come down. Here's the question. What happens when it comes down? Does it meet this point here? That's one possibility. Another and if that happens, we call them cycles. That means predators and prey will go in cycles. Okay, their numbers will increase, decrease in a periodic way, but eventually they just keep on doing this. So this is one possibility. Now there is no easy way to know that from this diagram alone. One has to really do calculations. Okay. And what's the another possibility? Just think about it in a more of a flow, in terms of flow and topology here. What are the other possibilities?
It's spiral inside.
It could spiral inside. So, okay, for example, what Ahmed is indicating is something like this could happen. Something like this can happen. So we call them spiral, as he rightly said. That is spiraling inside. In which case, this would be what would this be in that case? This equilibrium will become a stable equilibrium. Okay. What happens if what's the opposite of this? Spiraling outside.
Outside.
It can also spiral outside like this, and eventually maybe it will hit this. So if it's spiraling outside, the only possible scenario is it actually will have to hit this eventually, right? There's nothing else that can happen. As you can see, there are three possibilities: cycles, spiral out, eventually leading to extinction, and then spiral in, lead to equilibrium of NP. Okay, spiral. So it will be a stable equilibrium. Okay, this is also a stable equilibrium, but it just spirals in. As you can see now, the spiraling behavior is a property as well as both the cycles. Just to step back a bit and think more generally, cycles and spirals are properties that can happen only in two species systems. They cannot happen in one species system. Could this have happened in in an equation of the form n dot is equal to f of n? Okay, so that's not possible at all there, because from the equilibrium there were only two ways: it could flow out or flow in, right? There was nothing else that was possible there. But here we are actually multiple possibilities here. There are new types of equilibrium and dynamics possible. That was not possible in the one species system. But here is a small catch though. Remember that the logistic model, the first logistic model we studied, did have both spiraling in sort of, right? Spiraling out as well as cycles, right? So you know, in one species you can of course have cycles only, you know, but only if we have, you know, sorry. So I just want to make some general remarks on dynamics here. Now, one species.
I had a question.
Yeah.
So, I mean, generally, it's like that, say, one prey is for so many predators or something like that, right? I mean, somehow is that taken care or that's not?
That's a very good point. So here what we are studying is a specialist predator. So this predator depends only on this prey, because if n is 0, right? If n was absent, what happens to the predator here? N will be 0, meaning this term will be 0. We have only minus dp term, that means there's only a death term of predators. So therefore, this predator will die. So that's a very, very good point. So we're actually modeling a specialist predator. Specialist predator means, you know, it's specialized to prey on a very specific species. And we are looking at the dynamics between that species and this predator. Okay. Of course, it's possible that this prey has, now, is it possible that this prey has multiple predators? So we are again not considering that. It's basically a specialist predator prey dynamics. So this prey has only one predator and this predator has only one prey. Okay, and these kind of systems are typically present in, you know, tropical, not tropical, you know, temperate areas. You know, for example, in, you know, cold deserts, you have literally one type of fox and one type of rabbits. Okay, and nothing else. So, you know, they depend on, you know, so then these kind of models are really applicable in those cases. Okay.
So
yeah,
in the PN graph, can't the spiral expand as in be an outward spiral?
But you know, if it goes out, it has to somehow come back in, no? Unless it shrinks in this region, it will go and hit this, right?
I see, okay.
Or then I wouldn't call it spiraling out though. Spiraling out is also possible to just go towards infinity, but that means there's no limitation, no? How can things go on just infinitely large? So, I mean, one possibility is, you know, maybe it will go spiral out like this in the horizontal x-axis. When the predator goes to 0 and then will just keep on increasing. That's in principle possible. That doesn't quite happen in the system. Okay. So one species. Okay. So the general remarks here, what are all the possible dynamics? You know, one species, we remember that if we had a discrete time dynamics, we had stable equilibrium, cycles, and chaos, right? But the moment you had continuous time, we only had equilibrium. Cycles and chaos. Could they happen? It was not possible at all, right? Okay. Now, if you now look at two species, of course, discrete time has everything anyway possible. So, you know, there's no need to even study discrete time in two species. So when you have continuous time, this is how now of course you can have stable equilibrium. You can have now spirals that lead to stable equilibrium. Okay. Now you can have cycles, and it turns out that chaos is still not possible in continuous systems. Only in 3 species continuous time systems, chaos becomes possible. Not always, of course, you still have stable equilibrium and everything is possible. Everything is possible. Then that's when this is a possibility. Okay. So what this also shows is the discrete time dynamics shows the level of complexity at a single species that is possible only with 3 species in a continuous system. It's really worth thinking. Why do you think this might be happening? I won't answer this question to you. It's really worth thinking. Forget about chaos. How is it that cycles were not possible in continuous time, but they're somehow appearing in 2 species continuous time? Okay, whereas 1 species discrete time actually allowed cycles. How is that? What is it about the mechanism that are possible in discrete time 1 species that can happen only in 2 species continuous, but not in 1 species continuous? Okay, I really leave that as an exercise for you to think about. Okay, so going back to this, these are all the possibilities that can happen for the load covered Terra system, but it turns out that for the specific model we have written down, the answer is actually this. So what we have are basically cycles. Okay. So it's neither a spiraling in or spiraling out, it's actually a cycle. Okay. Now, yeah, any questions?
How can you tell when it's going to cycle and when it's going to spiral out or spiral in?
So okay, now how do we tell? So let's just do that. How do we tell? So how do we know? I don't know if this if it's actually making it harder for you all to read or easier to read with all these rulers. Okay, so how do we know? So you remember the Jacobian matrix I mentioned? So, remember that if you had an equation like this, a single species system, how do you find the stability? You just compute the derivative of f at the equilibrium, right? And you look at the sign. But the moment you have a more complex, 2 species system, okay, then you have first of all 2 functions and 2 variables. So you will have to basically compute. So let's call species as N1 and N2 and the functions as F1, F2. So you'll have to compute this matrix first, which is called the Jacobian matrix. And you evaluate this at the equilibrium, whichever equilibrium you are interested in. So in the Lotka-Volterra model, there were 2 equilibrium. One equilibrium was the extinction equilibrium. The other equilibrium was that coexistence of predator-prey equilibrium. And then find the eigen values of J. Okay. And then, now there are many possibilities now. Case 1. Okay, let's call them lambda 1 and lambda 2. So if you have a 2 by 2 matrix, there are only 2 eigenvalues that are possible. And these 2 eigenvalues can be real or complex. Okay. Okay. Now, if lambda 1 and lambda 2 are real, and if lambda 1 is less than 0 and lambda 2 is less than 0, both the eigenvalues are negative. So that corresponds to what we had here. If this was less than 0, we call them stable, right? For single species. Now for 2 species system, if both the eigenvalues are real and less than 0, then we have a stable equilibrium. Okay, That's the first scenario. I think I mentioned this last time. Now, a second possibility is that lambda 1 and lambda 2 are not real, are complex, which means they have form like, 1 plus 2i. It's a minus 1 plus 2i, for example. Okay. So then what you need to do is check if the real part of lambda 1 is less than 0. And likewise, the real part of lambda 2 is less than 0. If both of them are less than 0, for example, in this case, real part of this complex number is minus 1. It is less than 0. If both of them are less than 0, again, we have a stable equilibrium. Now, you might ask, what is the difference between the stable equilibrium of case 1 and case 2? Can anybody guess?
These two will have spiral.
Exactly. So case 1 will look like this. Okay, this is N and P, hypothetically. Let's say this is the equilibrium. Okay. So if for this equilibrium, if both the eigenvalues are real, and if they are both negative, then the trajectories will look like this. The perturbation you make will go like this. Okay. On the other hand, for the case 2, they will go like this. Okay. So do you understand the difference between the two? Now there's a third case. There are many more cases, by the way, by no means just 3 cases. So the chapter 5 in Strogatz covers, I think chapter 5 or 6, I forget. I think it's 5. I think I mentioned in the last last system also. Okay. So consider the third case when lambda 1 and lambda 2 are complex, but a very special type where the real part are basically 0. So this is analogous to f prime n star being equal to 0. So therefore, you can't really say if it's stable or unstable anymore. Okay, so you don't know. So in this case, something may happen. In this case, there are 2 possibilities. In this case, one possibility is that it is actually stable or unstable depending on what the higher order terms do. Actually, there are 3 possibilities: stable, unstable, and a third thing called mathematically it's called centers. What that, it's precisely this thing that actually happens in the case of Lotka-Volterra model. So what does this mean? It means the following. It means these kind of trajectories happen. N, P, this is the equilibrium. Okay, so now what happens is that it just goes in circle like this. If I now make a perturbation, let's say if I made a perturbation, what happens? It doesn't come back to this. It just makes a new circle now. If I made another perturbation, it just makes a new circle now. Sorry, usually any 2 circles will never intersect, by the way. Okay, so basically, depending on the initial conditions, they will just go in circles. They won't spiral in or spiral out. Okay, and in fact, this is precisely what happens for the Lotka-Volterra model we have just studied. Okay, now there are, yeah, go ahead.
Do they have to be circles or can there be any closed shape?
No. In this case, they are called, I'm sorry. They are called centers, but you're right. They could be any closed shape. They could be ellipses. They could be basically a loop, any loop. And a loop shape will depend on the sort of, the various parameter values you have. Sorry, thanks for correcting me. They're not necessarily circles.
What would happen when the cycle hits the n is equal to 0?
It does. Okay, it doesn't hit. I mean, okay, if it does it, of course it gets stuck there. because once n is 0, p will also fall to 0, right? So, but as long as you don't start with that initial condition, it can never really reach there.
Okay.
Now there are more possible scenarios. Now what happens if the real values of lambda 1 and lambda 2 are positive? So that's when you say any of them. It doesn't have to be one. Even if one of real values of lambda I is greater than 0. So this would basically means that the equilibrium is unstable. Now there are many possibilities. Now that means you can't say much more about this equilibrium anymore. It might go to some other equilibrium which is stable if you push away from this equilibrium. Now what is very interesting is the following. Again, let's compare with one species system. Okay. Compare with in one species system. Let's say if I'm going to plot n as a function, f as a function of n, f is the right hand side, the entire growth function. Let's say this looks like this. Okay, what is this equilibrium? This is an extinction equilibrium. What is this? Is it stable? So if I make a perturbation, it's a growth rate negative, it is stable, right? What is this? The intermediate equilibrium. Is it stable or unstable?
Unstable.
It's unstable, right? Because any perturbation I make here will grow. Anything I make below will decay. What about this equilibrium?
Stable.
Stable. So you see an interesting pattern. Hypothetically, imagine there was one more equilibrium here. Can you close your eyes and say, what should this be?
Unstable.
This has to be?
Stable.
Huh?
Unstable.
Unstable. So stable, unstable, stable, unstable. That has to be the case. Okay. So basically any two consecutive equilibrium have to be of opposite type in terms of stability. And if there are only two equilibrium, one of them has to be stable, other has to be unstable, right? But that's not true when you have a two species system. So you can have an extinction equilibrium that is unstable. You can have a coexistence equilibrium that's actually unstable. Both of them can be unstable. So what can happen in such a case? Can you imagine? So one scenario is what you have already seen, by the way. This was actually neither unstable nor stable, right? And real part of the eigenvalue was 0. But what I'm saying is this: real part of eigenvalues of both of these equilibrium are positive. So what does mean? This will now push away. This also will push away. One interesting concept, one obvious consequence is they will just go somewhere else. The final trajectory may be somewhere else. Okay, that's one possibility. But one other interesting thing can happen, which is that it actually again goes in loops like this. So these are called limit cycles. So limit cycles are basically the ones that circle around, not circle is not necessarily in the circular sense, they basically loop around unstable equilibrium. Okay. Okay, so that's another interesting possibility that's possible that can happen in two species systems. They're called limit cycles. Okay, and identifying them actually is slightly more difficult. Okay, you can't, for example, eigenvalue analysis of both of the equilibrium doesn't tell you about limit cycles directly. So you have to sort of work a bit harder, and that requires more analysis, which I will not be covering in this class. Okay, so these are the possibilities that can happen in two species systems. This is also why I don't try to go too much into two species systems, because it mathematically becomes slightly more involved. And but for those of you who are interested, the book by Strogatz or even any book on theoretical ecology usually has these things.
What is the difference between centers and limit cycles?
So centers are they are more like neutrally stable. If I push a center, it just makes another loop, which is a different loop from the previous one. A limit cycle is actually a stable cycle. So basically think of centers as neutrally stable orbits. whereas limit cycles are stable orbits. So which basically means if I make a perturbation, let's say deep a little bit inside, it will actually then slowly converge to this. If I make a perturbation outside, it again will converge to this. Okay, and in fact, so let me just also summarize and tell you that if you go back to 3 models here, okay. So in this model, let me just, because these are all things I'm not covering in terms of mathematical details, so let me just state the results. So here you will find centers, or basically in terms of ecology, they're basically predator prey cycles. However, very interestingly, the moment you go to low Volterra model, which has this carrying capacity for the prey, centers disappear. Oh, it's not centers, it's centers. Okay. So here, what you have is basically a stable equilibrium of Pn. And if I'm right, I think it's actually a spiral. Okay. Here, there are actually no cycles at all. However, interestingly, the moment you introduce this functional response, okay, you of course still have stable equilibrium for some parameter values, but you also have limit cycles. Okay, which basically means predator prey cyclical dynamics. So what this shows is that including functional response actually destabilizes predator prey systems, and now they become a cyclical system. Okay. So what I will try to do is I will try to send an R code where you can do numerical simulations, okay, of all of this, okay, to get some intuition of how the dynamics plays out. But do see if you can, it's worth trying out for yourself. Can you do this Jacobian analysis? Basically, can you construct the Jacobian by doing simple derivatives? And then can you find the eigenvalues, okay, in general? So if you remember your high school matrices, you will have to revise that to be able to do this, okay? But in the exams and all, don't worry, I'm not going to bother with these kind of questions. Okay, any questions? Is Friday a holiday, by the way?
It depends on the moon.
We don't know, right? Okay. So if it's a holiday, I think as of now it is listed as a holiday. So if it's a holiday, there will be no class. So so unless registrar IAC sends a notification changing the holiday, I'm going to assume it's a holiday. As of now, it is IAC's calendar says it is a holiday, right? Okay. So tentatively there is no class, there's no lab on Friday. Okay. So we'll meet next Wednesday, unless the holiday plan changes. Okay. Okay. So if there are no questions, I will stop here.
Thank you.
But if you have questions, feel free to ask.